p. Remember, this is uniform, so this is 1. So this is not minus infinity to plus infinity. In our problem, 0 to 1. And so we have to solve this integral. So if you look at a beta distribution is some constant multiplied by this. So from there you can easily get the, I think this is, what is it? Let me just check. I think that's what it is. Beta distribution is this n plus 1 factorial divided by that. Or you can directly do it. Substitute p equal to sine theta, sine squared theta. So this will be 1 minus sine squared cos squared theta to the power. dp will be 2 sine theta cos theta, and just look up tables. You'll get this value. So this is, you need to compute, make sure you understand this. So if that is the case, I can update it here directly, right? So this is going to be n plus 1 factorial. This is the denominator, k naught factorial, n minus k naught factorial. Suddenly the problem gets complicated, you see. So this is the, I just substituted for this. This is 1. Right? So this is, so if you draw that below this, it's going to look like something like, it will sort of, that means these values are now more likely. So this is the updated with the A. This is also a beta distribution. Okay, now, so how to update FP? I just told you. So we updated this as, so this is done. Now what? So now naturally the assumption is we would, we being here, whatever you want to predict next, which density function would you use? This or this? Obviously we spend money to get here. So everything, so this is where the prediction comes. We would use this to do all the forecasts. This is where you can see the importance of data. If you collect bad data, you get bad density function. Because there is only so much the techniques can help you. If your data collection is garbage, all this is... all right, so let me define C to be you have to realize the context. We are not here. We spent a lot of money, collected the data, we are here. We got the new density function. So when you say head in next toss, the next is after collecting all this data, so we want probability of C. Somewhere here, didn't we have this formula? Here. Probability of any event, look at here. Probability of any event, C is probability of C given x equal to P multiplied by FPP. Right, so this is true. Yes, x equal to P. But as I said, you have to realize the context. Which probability density function would you use here? New one. That's the whole point. Because if you go back and say, I'm going to use uniform, what are we doing here, right? So we collected the data. So this is where, so here of course I will use the updated density function. If you have more data, you can update it. But remember, what is this? If the, read this, this says, what is the probability of getting ahead given that the value of P is P? Then this is going to be If probability of getting a head is P, then head in next toss will be P itself. So this is small p. So this is small p multiplied by this density function, which is what is it? N plus 1 factorial. So here, I'm not going to use the uniform, I'm going to copy from there. What is p to the power k naught, q to the power n minus k naught dp, 0 to 1. So I hope you see the logic. If you are careless and if you put here just uniform, then you are not taking advantage of the fact that the data. So the data is used to compute the new density function. And we use the new density function to forecast, because the new density function is more reflective of the coin than the old. So this is with no knowledge. This is after learning. All right, so we need to, I pull out the constants. So n plus 1 factorial, k naught factorial, n minus k naught, and this is 0 to 1, p to the power k naught plus 1, 1 minus p to the power. So I hope you understood the logic here, right? This is simple. This is C is simply probability of getting a hit in the next toss. All the tosses are independent. Given that x is what? X is of course the random variable representing probability of getting a head. So if x is given to be p, then this is just a small p. All right, now what about this integral? Look at that. That integral is very close to this, except k naught is replaced by k naught plus 1. So if I rewrite, look at, I'm going to do a small trick here. N minus k naught, I'm going to write like this. Why did I do this? Because then this integral looks exactly the same as this. So all I have to do is replace k naught by k naught plus 1. So this result is going to be k naught plus 1 factorial. This minus this, that is still n minus k naught factorial, divided by wherever I had n, I have now n plus 1. So this is n plus 2 factorial. So you can do some cancellations, and this will turn out to be k naught plus 1 over n plus 2. So we have an exact answer to the prediction. So what was the problem? Problem was the last line. If you toss the coin again, what is the likelihood of getting a head? That probability is k naught plus 1 over n plus 2. As I said, let me put some numbers. Let's say we did 98 tosses earlier, and k naught turned out to be 59, let's say. I'm just making up numbers. And so already at this stage itself, you know that, okay, out of 100 tosses, 60. So already it's a biased coin, you could say. So maybe here you would say the 59 divided by 98, that's not the answer. And so we know that's a biased coin. The question is how much bias, or how exactly biased it is. The answer is here. So this is going to be, the next toss it is going to be 60 over 100, 0.6. So we know the exact answer. So rather than say it's a likely biased coin, this procedure gives you to answer this exactly, I hope. Right? The 60 over, so this comes down to be 0.6. So you can see Bayes' theorem together with conditional probability density functions allows you to make a further inference into the future. And this is sort of an illustration. And this is the way you respect the data. So the data is used to update the density function. at every stage. And of course, then you use the new density function to make the predictions and so on.